Hey everybody, and welcome to this video on shifting graphs left and right. So let's make it happen. Alright, so here's our graph of the equation y equals 2x. Of course, it's a line with a slope of 2 and a y-intercept right on the origin, the point 0, 0. And there are some ordered pairs on the graph and captured in a table of values on the left. Now what I'd like you to do is if you would pause the video and please graph on your own the new equation y equals 2 times the quantity x minus 4. And if you'd please fill out the new table of values. Now let me urge you, please graph this new equation not by putting it into slope-intercept form, but please use a variety of x values and substitute them into the equation to find your corresponding y value and find new ordered pairs. Alright, so it appears that our new graph looks exactly the same as our old graph did, but shifted exactly 4 units to the right. Now we've definitely seen this before, but I want to take some time to delve deeper into the ordered pairs and how they've changed as a result of changing our equation and replacing the x with an x minus 4. So for instance, on the blue graph, consider the ordered pair 1, 2. And of course, if we substitute those values into their variables in the equation y equals 2x, 2 equals 2 times 1. Of course they make that equation true. That's why they're on the blue line. But now, if we have the exact same y value of 2 in this equation in red, y has to equal 2 times 1. We need x minus 4 to be 1 now. That means x has to be 5. Before, x had to be exactly 1 in order to make y 2, but now to make y 2, x has to be 4 bigger. X has to be 5. For the exact same y value, the x value had to be 4 larger. And that's why this point 1, 2 moved 4 units to the right over to 5, 2. Let's pick another point. How about the one on the origin? For the graph in blue, that contains the point 0, 0. 2 times 0 is 0. That's why it makes that statement true. That's why it's on the graph in blue. But now if we think of getting that exact same y value for our equation in red, of course x can't be 0. X is going to have to be 4. So that 4 minus 4 is 0, and 2 times 0 equals 0, making that statement true. For the exact same y value to be on the graph, the x value had to be 4 larger. That's why this point 0, 0 moved to the right 4 units to 4, 0. And in fact, that's what happened all over this graph. In order to get the same y value for this equation in red, the x value had to be exactly 4 larger than it used to be for our equation in blue. And that's why every point has shifted exactly 4 units to the right, because they have the same y value, but an x value that's 4 larger. Replacing the x in our equation with an x minus 4 had the effect of shifting our graph exactly 4 units to the right. Alright, let's try another example. Here's our familiar graph of y equals negative 3x. It has a slope of negative 3, and of course the y-intercept is right on the origin at 0, 0. And here are some ordered pairs, both on the graph and a table of values. And what I'd like you to do is I'd like you to pause the video and please graph on your own and fill out the table of values for the new equation, y equals negative 3 times the quantity, x plus 5. Again, I'd prefer you to graph this not by putting this equation in a slope-intercept form, but by using a variety of x values in this equation to find their corresponding y values. Doing so will help highlight the relationship between these two graphs a little better than putting this in a slope-intercept form. Alright, well it appears to me that this new graph in red looks exactly the same as our graph in blue, but shifted to the left 5 units as a result of replacing our x in the original equation with an x plus 5. But I still want to do a little bit more investigation as to why that's happened. So let's look at some ordered pairs and compare them. For instance, on our graph in blue, the ordered pair negative 2, 6. Of course, if we take those values and substitute them into our original equation, y equals negative 3x, negative 3 times negative 2 is 6. That ordered pair makes this equation true. That's why it's on our graph in blue. But now if we want to get the exact same y value for our graph in red, so if y were 6, we need to be multiplying negative 3 by negative 2. But no longer is it the case that x has to equal negative 2. X plus 5 has to equal negative 2. So obviously x has got to be negative 7. It has to be 5 less than it was in our original graph in blue. So for the exact same y value, the x value had to be 5 smaller. And that's why this ordered pair negative 2, 6 move to the left 5 units to negative 7, comma 6. One more real quick example. Of course, how about the ordered pair 0, 0 on our original graph? Of course, 0 equals negative 3 times 0. That's why it makes this blue equation true. That's why it's on our blue graph. But if we want to get a y value of 0 on the graph in red, of course, we need to be multiplying negative 3 by 0. X can't be 0. X has to be negative 5. It has to be 5 less than 0. It has to be 5 less than it was in our equation in blue. And so for every y value to remain the same, all the x values have to be exactly 5 smaller. And that's what takes all these ordered pairs and move them to the left 5 units. And hence, replacing the x in our original equation with an x plus 5 had the effect of shifting our graph to the left by 5 units. Alright, so here's a familiar graph, y equals 1/3 x. Of course, it has a slope of 1/3 and a y-intercept of 0. And here's some ordered pairs, both on the graph and a table of values. What I'd like you to do is take a moment to pause the video and please graph the new equation and make a table of values for y equals 1/3 times the quantity x minus 5. Again, please do so by substituting in a variety of x values and finding their corresponding y values. Alright, it appears to me that replacing the x with an x minus 5 in our equation gave the exact same graph but shifted to the right by 5 units. And if we look at the table of values, in order to get the exact same y value, all of our x values for our equation in red had to be exactly 5 larger than the x values were for the equation in blue. That had the effect of taking every single one of these ordered pairs and moving them to the right 5 units. Replacing the x in our equation with an x minus 5 had the effect of shifting our graph to the right exactly 5 units. Alright, last example before we generalize. Here's a graph of the equation y equals 3/2 x. Of course, it's got a slope of 3/2 and the y-intercept is right on the origin at 0, 0. And here's some ordered pairs both on the graph and in a table of values. And what I'd like you to do is to pause the video and please graph and make a new table of values for the new equation y equals 3/2 times the quantity x plus 4. Again, please do so by substituting x values into this equation and finding the corresponding y values. That'll really highlight the difference better than putting this in a slope-intercept form. Alright, when we graph this new equation, it appears that we get the exact same graph but shifted to the left exactly 4 units. In order to get the same y value, the x value for our equation in red has to be exactly 4 less than it was to get that same y value for our equation in blue. And that had the effect of shifting every point on the graph to the left 4 units because they all have the same y value, but the graph in red has an x value that's 4 less. Replacing the x in our equation with an x plus 4 had the effect of moving our graph 4 units to the left. Alright, now that we've got to investigate a whole bunch of examples, it's time to generalize our findings. Suppose that we have an equation involving x, or our independent variable, and y, our dependent variable, as well as a graph for that equation. If we replace the x in the original equation with an x minus k, this should shift our original graph to the right by k units. And if we were to replace the x in the original equation with an x plus k, this should shift the original graph to the left by k units. Now note, so far we've only investigated graphs that were lines, but this change in the equation is going to have that same change in the graph no matter what graph we're looking at and no matter what equation we're looking at. And we're going to explore a couple of those examples right now. So here's the equation y equals x squared minus 6x plus 7 and the graph that goes along with it. Now, if we wanted to graph the new equation y equals x minus 2 squared minus 6 times the quantity of x minus 2 plus 7, all we'd have to do is take all the x's in our original equation and replace them with an x minus 2. The big difference here from the ones we did before is that x happened to appear twice in our original equation. So every time x appeared there, we've replaced it with an x minus 2 in our new equation in red. And not surprisingly, replacing the x in our equation with an x minus 2 has the effect of shifting our graph exactly 2 units to the right. So here's the graph of our equation, y equals the absolute value of x plus 2. Now, if we wanted to graph the new equation, y equals the absolute value of x minus 4 plus 2, all we've done is taken the x in our original equation and replaced it with an x minus 4. And not surprisingly, replacing the x with an x minus 4 has the effect of shifting our graph exactly 4 units to the right. Alright, last example. Here's the equation x squared plus y squared equals 16, and the graph that goes along with it. It happens to be a circle. Now, if we wanted to graph x plus 5 quantity squared plus y squared equals 16, well, the only difference between these equations is that we've replaced the x in our original equation with an x plus 5. So, replacing the x with an x plus 5 should have the effect of shifting our graph exactly 5 units to the left. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.